Welcome to the next session, my dear students. In the previous sessions, we have discussed all the concepts related to treatment of water, and now we are going to do all the previous gate questions in this session. Okay, from this session onwards, we have left 3 questions in quality parameters because those concepts we have discussed later. That is why we didn't solved those questions. We will do it now. Okay, quality parameters in 2.3. Quality parameters 2.3 quality parameters of water. So in this topic, question number 17 and 18 we didn't solve. Let us see the question number 17 and 18 common data question. Question number 17 and 18, GATE 2003, 4 marks question. GATE 2003, 4 marks. So the question is like this, it is on alum dosage. A water treatment plant treating 10 mld of water requires 20 mg per liter of a filter alum, Al2SO4 thrice 18H2O. The water has 6 mg per liter of alkalinity as CaCO3. Then total alkalinity required. What is the total alkalinity required to match the filter alum shall be? So what is the given data? What is the given data? So given data is the quantity of water treated. So it is treating a quantity Q is equal to 10 mld. This much is water being treated in the treatment plant and the alum dosage is how much? Alum dosage is 10 mg per liter, 20 mg per liter. Alum dosage is 20 mg per liter. Alum dosage 20 mg per liter. The water has already alkalinity in it, so existing alkalinity existing alkalinity existing alkalinity is 6 mg per liter. Existing alkalinity 6 mg per liter. Total alkalinity required. So the first question was, the 17th question is total alkalinity required is equal to how much? Okay. So here total alkalinity as CaCO3, he is asking it as CaCO3, and this existing alkalinity, the existing alkalinity is also as CaCO3. This is as CaCO3. Okay. Now we have already derived the requirement of CaCO3 for x mg per liter of alum. Okay. So that means 666 parts of alum, 666 parts of alum needs 486 parts of alkalinity as CaHCO3 twice. But not here, it is not CaHCO3 twice, it is CaCO3. So in turn 486 parts of alkalinity as CaHCO3 needs 300 parts of alkalinity as CaCO3. That means, so 666 parts of alum needs 300 parts of alkalinity as CaCO3. So 1 part needs 300 by 666 parts of alkalinity as CaCO3. So if it is x mg per liter, then it is 300 by 666 into x mg per liter as CaCO3. So here this x is given as 20. So x is given as alum dose. So for 20 mg per liter, alum needs 300 by 666 into 20 mg per liter alkalinity as CaCO3, as CaCO3. So if you solve this, we will get the answer. We will get it as so 3 into 100 by 666 into 20, that is 9 mg per liter. We will get it as 9 mg per liter as CaCO3. This is the first question answer. So total alkalinity required as CaCO3 is 9 mg per liter. 9 mg per liter. So let us see the second question. What is the second question? Second question is quantity of quicklime required. So for preparing this much of alkalinity, how much quicklime is needed? How much quicklime is needed? Okay. For giving 9 mg per liter of alkalinity, for providing 9 mg per liter of alkalinity as CaCO3, for providing 9 mg per liter of alkalinity as CaCO3, how much quicklime is needed? Here the second question is quicklime shall be, so quantity of quicklime needed 10 to the power of 6 mg, that means kg per year. Okay, quicklime, 18th question is quicklime CaO needed in 10 to the power of 6 mg per year, that is nothing but kg per year. This is nothing but kg. Okay, now see here, total alkalinity required, total alkalinity required is 9 mg per liter. Okay, now existing alkalinity, existing alkalinity is equal to how much? 6 mg per liter. Existing alkalinity is 6 mg per liter. So alkalinity needed from external source, alkalinity needed from external source is how much? 3 mg per liter. So already in the water there is 6 mg per liter of alkalinity already present. So the remaining gap we need to give from the external source, that is 3 mg per liter. Now for providing 3 mg is needed for 1 liter. 3 mg is needed for 1 liter. So here we are treating how many liter? 10 million liter. So for 1 liter For 1 liter, we need 3 milligram. Okay, here how many liter are there? 10 million liter. For 10 million liter per day, we need 10 into 10 to the power of 6 liter. Okay, 10 into 10 to the power of 6 liter into 3 mg. This is per day. This is per day, but we want it for year. So for 1 year, we need 10 into 3, that is 30 into 10 to the power of 6, okay, milligram. So if I convert this into year, this is 1 by 365 year. 1 day is nothing but 1 by 365 year. So multiply here with 365, then it is year. 1 by 365 year. So now this is the answer. If you solve this, you will get the answer as 30 into 365, that is the answer. 30 into 365, that means I think it is 2132. So 6132. And here one more thing, a small correction we need to do. Small correction. 1 second. Here actually I made a small mistake. Here it was quicklime CaO. Here this is 9 mg per liter as CaCO3. I wanted to convert this alkalinity 3 mg per liter. These are all as CaCO3. Okay. This is as CaCO3. Now what is as CaO? So 3 mg per liter. So here one part of CaCO3, okay, 100 parts of CaCO3, 100 parts of CaCO3 needs 56 parts of CaO. Okay, so one part needs 56 by 100 CaO. Now 3 mg per liter needs 3 mg per liter CaCO3 needs 3 into 56 by 100 mg per liter of CaO. Actually we want CaCO3, but we are procuring CaO. So that means we have to convert this 3 mg per liter requirement as CaCO3 into the requirement in terms of CaO. So 3 mg per liter of CaCO3 needs this much CaO. So this is for 1 liter. This is for 1 liter. So for 10 million liter, for 10 into 10 to the power of 6 liter per day, it will be, the requirement will be 10 into 10 to the power of 6 into 3 into 56 by 100. Okay, by 100 mg per day. Mg per day, but I want it for year. I want it for year. So for 1 year, the requirement will be 10 into 10 to the power of 6 into 3 to the power of 3 into 56 by 100 into what is this day? 1 day is nothing but 1 by 365 year. So 1 by 365. So this 365 will come up. So this will be equal to 6132 kg per year. 6132 kg per year, or 6132 into 10 to the power of 6 milligram per year. Either this or this, both are correct. So 10 to the power of 6 milligram is nothing but 1 kg. Okay. So this is the 17th and 18th question, which we haven't discussed in the previous chapter. Okay. Am I clear? So simple, I would like to repeat it again. Please listen carefully. Alum dosage is given. Existing alkalinity is given. Total alkalinity required is asked. As CaCO3, both are as CaCO3. So now, if it is 666 parts, needs 300 parts, this formula I have used. So using this formula, I got this answer as 9. This is the total alkalinity requirement as CaCO3. So now he is asking what is the amount of quicklime needed in 10 to the power of 6 mg per year. Okay. Now total alkalinity is this, existing alkalinity is naturally presenting alkalinity is this, external alkalinity needed is 3 mg per liter, but this is as CaCO3. I want to convert this into CaO. So 100 parts of CaO needs 56 parts. Then 1 part is 56 by 100. So 3 parts needs 3 into 56 by 100 mg per liter as CaO. So this is for 1 liter. So 1 liter 3 into 56 by 100 mg is needed. So these many liters I need to multiply it with that, and that is for 1 day. So if it is 1 year, multiply it with 365. Then you will get the requirement for 1 year in kg per year or 10 to the power of 6 milligram per year. Both are same. So let us discuss the next question. Question number 32. Question number 32. Question number 32. It is from chlorination. Anaerobically treated, it is GATE 2011. GATE 2011 1 mark question. Okay. So anaerobically treated effluent has MPN of total coliform as 10 to the power of 6 per 100 ml. After chlorination, the MPN value declines to 10 to the power of 2 by 100 ml. So the present removal percentage R and log removal log R of the total coliform is. See here, what is the given data? Given data is, so initial organism concentration of bacteria or microorganism, it is 10 to the power of 6 number per 100 ml. Okay, after treatment it is 10 to the power of 2 numbers per 100 ml. So what is the efficiency? Percentage R. What is the efficiency he is asking? Efficiency is nothing but what? N naught minus NT by N naught into 100. This is efficiency, right? So 10 to the power of 6 minus 10 to the power of 2 by 10 to the power of 6. It is simply, if I take 10 square common, 10 square into 10 to the power of 4 means what? 10,000 minus 1 by 10 to the power of 6. So 10,000 minus 1 is how much? 9,999. So into 100. So here it is into 100, is also into 100. So which is equal to, so again this will be cancelled, 9,999 by 100. It is 99.99%. This is the efficiency of the removal, normal efficiency. So what is log removal? I told you already. Log removal, it is equal to log R is equal to log N naught minus log NT. So log N naught means how much? Log to the base 10, N naught is 10 to the power of 6 minus log NT 10 to the power of 2, which is equal to 6 minus 2, that is equal to 4. So the log removal is 4. The log removal is 4 and the normal removal is 99.99. So looking at the options, option number C is the answer. So this is log removal and this is normal removal. Okay, this is question number 32. This is question number 32. So these are the questions we left in the previous chapter because these concepts belongs to the treatment of water. So now we are entering into the real questions into the chapter treatment of water directly. 3.2. Treatment of water. So in this question number 1, 2001 GATE 1 mark. GATE 2001 1 mark question. Question number 1. It is a theoretical question. Aeration of water is done to remove. So what aeration will do? Aeration of water is done to remove. Generally aeration is necessary to remove dissolved, okay, to remove dissolved ions and dissolved gases. Majorly dissolved ions and dissolved gases. Dissolved ions means Fe2 plus, Mn2 plus, okay, NO3 minus. So likewise some kind of dissolved ions can be removed by aeration, and dissolved gases means CO2, H2S. Similar, these kind of gases can be removed under aeration. So if you look at the options, first option is suspended impurities, wrong. Dissolved impurities it will remove. Color, indirectly it remove but not directly. By removing the iron and manganese it will remove the color. Okay, dissolved salts. See, dissolved salts never removed by aeration. Dissolved ions, salts are stable. Salt will be present in an insoluble form which can be removed in sedimentation or any other location. So aeration cannot remove salts. Okay. Dissolved gases. See, dissolved gases are removed by aeration. So this is correct. Dissolved gases is correct. Not dissolved salts. And color is not directly removed. Indirectly it is removed by removing dissolved ions. Okay. That is the answer of the first question. So let us go to the second question. Let us go to the second question. Question number 2, GATE 2019, 2 marks, set 2. GATE 2019 2 marks from set number 2, question number 2. Okay, so let us read out the question. A water treatment plant treats 6000 meter cube of water per day. As a part of treatment process, discrete particles are required to be settled in a clarifier. A column test indicates that an overflow rate of 1.5 meter per hour would produce the desired removal of particle through settling in the clarifier having a depth of 3 meter. The volume of the required clarifier in meter cube round off to 1 decimal would be. Okay, so what is the given data? Let us first extract the given data. So the given data is the quantity which we are treating per day, that is 6000 meter cube per day. This is the quantity which we are treating per day, right? Now, so discrete particle settling means it is type 1 settling. It is type 1 settling. A column test indicates that an overflow rate. So overflow rate means not V0 was given as 1.5 meter per hour. So 1.5 meter per hour. So this is V0. Okay. So the desired removal of would produce a desired removal of particle through settling. Okay. So clarifier is having a depth is given. So depth is given as 3 meter. Depth is given as 3 meters. So here we want to find the volume. So volume is how much? Okay. So the plan area or surface area of a clarifier or sedimentation tank is equal to Q by V0. Okay, Q by overflow rate. Q is 6000 meter cube per day. That means I want to convert it into meter cube per hour. Then I need to divide it with 24 hour by 1.5 meter per hour. Now it will give you the surface area or plan area, that is 6000 by 24 into 1.5. This is meter square. This is meter square, right? So how much it would be? 4000 by 24. That means how much? 6. It would be equal to 166.66 meter square. 166.66 meter square. So this is the surface area. Okay. Now we want the volume. So volume is simple. So volume is nothing but depth into surface area. So volume is equal to H into surface area, which is equal to 3 into 166.66. So approximately it will be how much? It is equal to 500 meter cube. It is equal to 500 meter cube. So that is the answer. This is the solution of the second question. This is the solution of the second question, right? So let us go to the third question. It is GATE 1992 1 mark. GATE 1992 1 mark. GATE 1992 1 mark question, question number 3. Here the clariflocculator is a unit in which the following things will occur. I already told you clearly what is clariflocculator. So clariflocculator will contain 3 things. One is rapid mixing. Okay, it contains three things. One is rapid mixing, that is nothing but coagulating. Next is slow mixing, that is flocculating or flocculator. And the third one is sedimentation. So these are the things which will happen in clariflocculator. Okay, so let us read out the solutions. Floc formation and its subsequent removal by filtration. No, filter will not come here. First option is wrong. Floc formation and its subsequent removal in sedimentation. So that is correct. Option B is correct. Floc formation, third option is floc formation and its subsequent removal by decantation. That is wrong. And also fourth one is also wrong because there he is saying chlorination. Right? So clariflocculator, so floc formed and that floc is sent into sedimentation tank. There it will get removed. So this is nothing but clariflocculator. Okay. Next is question number 4. It is also theoretical question. 1998 1 mark question. 1998 1 mark question. Question number 4. (1998) 1 mark question. So here coagulation, flocculation with alum is performed. Coagulation, flocculation with alum is performed immediately before chlorination. So when we perform coagulation and flocculation, when do we perform these two, coagulation and flocculation? So option A is before chlorination. So before chlorination. And option B is after chlorination. Immediately after chlorination and immediately before chlorination. And option C is after rapid sand filter, and D before rapid sand filter. So D is before rapid sand filter. So it is very clear that we perform this before rapid sand filter because so whatever the floc that is being formed, either it will be removed in the sedimentation tank, and if there is any unsettled floc, if it is present, that unsettled floc will be removed in the filter, rapid sand filter. So that is why before rapid sand filter we perform this coagulation and flocculation treatment. Okay, so next question number 5, 1998 2 marks. 1998 2 marks, question number 5. So it is a numerical. For a flow of 5.7 mld, that is million liter per day, and a detention time of 2 hours, the surface area of a rectangular sedimentation tank to remove all particles having a settling velocity of 0.33 mm per second. Okay, so what is the data given? So what is the given data here? So the given data is, so here the flow is given. So Q is equal to 5.7 mld. So Q is equal to 5.7 mld and a detention time of 2 hours. So dt is 2 hours. Detention time is 2 hours. The surface area of a rectangular tank to remove all the particles. So he is asking what is the surface area, okay, to have 100% efficiency. To remove all the particles means what? 100% efficiency is needed, having a settling velocity of 0.33. Settling velocity is given 0.33 mm per minute. 0.33 mm per minute. Mm per second. 0.33 mm per second, right? Now, so when the efficiency is 100, so we know that efficiency is Vs by V0. Efficiency is Vs by V0 into 100. So this efficiency is how much? It is 100%. So that means Vs is equal to V naught. So V naught is equal to 0.33 mm per second. So V naught is also equal to 0.33 mm per second. Now, if you know V naught, so surface area is equal to Q by V naught. Q by V naught, where Q is equal to 5.7 into 10 to the power of 6 liter per day, by V naught is given in 0.33 mm per second. So we need to bring the uniform units. Here. So here the answer is in meter square. So convert everything into meters. So if I convert that into meters, so 5.7 into 10 to the power of 6 into 10 to the power of minus 3 meter cube. And if I convert this day into seconds, that means 24 into 60 square. So this is meter cube per second. Similarly here also it is 0.33 mm. I want to convert it into meters. So 10 to the power of minus 3 meters per second. So if you solve this 5.7 10 to the power of 3 meter cube per second by 24 60 square to 0.33 10 to the power of minus 3 meter per second, then you will get the value of the surface area as 90. Question number 5. Yeah, it is 199.9 meters square. You will get 199.9 square meters, which is nearly equal to 200 meters square. Is nearly equal to 200 square meters or meter square. So that is the solution of the fifth question. Let us discuss the next question. Question number 6. Question number 6. It is a theoretical question, 2001 mark. 2001 mark question. So question number 6, 2001 mark question. So the question is, use of coagulant such as alum results in reduction of pH of the treated water, increase of pH of the treated water, no change of pH of treated water may cause an increase or decrease of pH. Okay. So when alum is reacted, Al2SO4 thrice 18H2O. So when this is reacted in the presence of alkalinity CaHCO3 twice, okay, it gives 3 CaSO4 3 CaSO4 plus 2 AlOH thrice plus 6 CO2 plus 18H2O. Okay, here if you see this compound, I already told you, when you add alum, this alum will form different components such as AlOH2 plus, okay, AlOH twice plus and AlOH thrice, which is the flock, and Al17OH21 4 plus, okay, so Al17, so Al17 OH21, like that some compounds it will form So everywhere it needs OH in it. Okay, everywhere it needs OH in it. OH in it. But this OH, when it is taking, so H plus ion is being released, because of which the water will become acidic. So the alum takes OH ions from alkalinity and releases H plus ions Okay, because of which so pH will reduces, because of which pH will reduces when water reacts with alum. Okay, so the option is results in decrease, or option A, results in reduction of pH of the treated water. So treated water will have less pH in it. Next question, question number 2001, 1 mark. Question number 2001, 1 mark question. Question number 2001. Question number 7. Question number 7. GATE 2001, 1 mark. Here the following chemical is used for coagulation. Very simple. The options are ammonium chloride, aluminium chloride, aluminum sulfate. It is very easy. Aluminum sulfate is used. AlSO4 thrice, Al2SO4 thrice. This is used as aluminum sulfate is used as alum. So 2001, the option is 1. Okay, so this is in this session we will discuss the rest of the questions. We will discuss from question number 8 in the next session. Thank you so much.